All right, this is the last section. This is the applications portion of Taylor polynomials. So what we're going to talk about is Taylor and Maclaurin polynomials, this thing which is called the Lagrange error, and some of the applications in order to be able to figure some things out to in a certain accuracy. So Taylor polynomials, Taylor-Maclaurin series, we're going to use those to approximate functions. So the more terms we can find, the better the approximation is going to be. That should make sense. Just like everything else, the more terms you go with something, the better your approximation is going to be. If you're asked to use a Taylor-Maclaurin polynomial to approximate a value of f of a, where f of x is the given function, and a is a value other than the given c value, you find the Taylor or Maclaurin polynomial up to the given n value, whatever they tell you. And then you plug a into the polynomial in order to approximate the value. And note, you can differentiate, integrate these polynomials, and this is equivalent to differentiating or integrating the function that is being approximated. So let's jump in to the examples. All right, so our first example says, approximate the natural log of 2.95 using a fourth degree Taylor polynomial for f of x equals the natural log of x, centered about x equals 3. It makes sense for us to center this thing at 3, considering we're trying to find the natural log of 2.95. So if we took the natural log of 3, that's really close to the natural log of 2.95. So what we need to do is we need to develop the Taylor polynomial centered at 3. It'd be really nice if it was a Maclaurin one, because I think we've already done the natural log of x for that, but we don't have it. It's a Taylor, so we have to develop this thing. So if you guys remember, there we go. For some reason it decided to go off there. You start off with the function at the center. So f of 3, plugging 3 into ln of x is ln of 3. Come on, there we go. We're going to need the derivative, f prime. So f prime of x, 1 over x. Evaluated at 3 is going to give us 1/3. We'll need f double prime. That's x to the negative 1, so we're going to get negative 1 over x squared. And evaluated at 3, we're going to get negative 1 over 9. Let's see, we need to do a fourth degree, so we need to go out to 4 derivatives. So third derivative is going to be, let's see, that's going to be x to the negative 2 here, so multiplied by negative 1 gives us 2. X to the negative 3, which is over x cubed. So 2 over 3 cubed is 27. And then we need a fourth derivative. Making that x to the negative 3 is going to give us negative 6 x to the fourth. So that's going to be negative 6 over 3 to the fourth is 81. And that does reduce. We don't really need to in this case, but it does reduce. So we have the 4 terms here that we need. So to write our Taylor polynomial of fourth degree, Taylor polynomial, fourth degree of x, centered at x equals 3, is the first term, natural log of 3, plus, it'll be 1/3 x minus 3 all over 1 factorial, plus negative 1/9 x minus 3 squared over 2 factorial, plus 2/27 x minus 3 cubed over 3 factorial plus negative 6/81 x minus 3 to the fourth over 4 factorial. No need to simplify any of this stuff right now, because ultimately what we're going to do is we're going to use this Taylor polynomial right here to approximate the natural log of 2.5. Well, 2.5 took the place of x. So down here, 2.95 is going to take the place of x. So when we go ahead and work this out, we get the natural log of 3 plus 1/3. I'm just going to simplify as we go. 2.95 minus 0.3 here is going to be negative 0.05. This is going to be minus a ninth divided by 2, so that's going to be minus 1/18. Again, it's going to always be negative 0.05, but the power will change, so now it's squared. 2 over 27 divided by 6. Is that right? Yeah, 2 over 27 divided by 6. 2 over the 6 is going to reduce to a third, so 3 times 27 is 81. So I'm going to get 1 over 81. Oops, not x. Minus 0.05 cubed. And then this last one, negative 6 over 4 factorial. 4 factorial is 24, so that's going to be a fourth. Fourth times 81 on the bottom here is going to be 324. So I believe we get 1 minus 1 over 324, negative 0.05 to the fourth. So what you can see here is this is a polynomial. And the only thing that I don't like about this problem in particular is the fact that we have to use the natural log of 3 as our first term. The rest of these you could actually figure out without a calculator. The problem is the natural log of 3 is not a commonly known value. So we'd have to use a calculator to actually do this. We're going to use a calculator for all this stuff anyway. So if you're doing this on your own while you're taking your notes, go ahead and plug these things into the calculator and then see that you get the same thing that we get here. What I got was 1.081805,209, I believe. This is what I get from my Taylor polynomial of fourth degree. Now, if all we're going to do is just plug in natural log of 2.95 into your calculator, you would see that what you get is 1.08180,517. What you should be able to see is by doing this Taylor polynomial of degree 4, all of this is identical. So we are actually exactly the same to 1, 2, 3, 4, 5, 6 decimal places, it looks like. That's a pretty good approximation, and we only went to the fourth degree Taylor polynomial to do that. Obviously, the further that we go, the closer and closer these approximations are going to be, and as a matter of fact, they will be exact if you did this for an infinite number of terms. So anyway, good approximation. I don't like the fact that we had to use the natural log of 3 in there, but it is what it is. All right. Next example. We want to approximate sine of 5 pi thirds using a fourth degree Taylor polynomial for sine of x centered at 3 pi halves. So again, this is centered at 3 pi halves. We cannot use the standard Maclaurin, so we have to develop this one ourselves. So the first thing is the function evaluated at the center. Sine of 3 pi halves, of course, is negative 1. Hopefully you guys know the derivatives of these, so I'm going to kind of skip writing that, but we're still going to write down what the derivatives evaluated at our center are. So I need the first derivative at 3 pi halves. First derivative of sine is cosine. Cosine of 3 pi halves is 0. Second derivative is going to be negative sine. So that should give us um, negative sine of 3 pi halves, which is positive 1. F triple prime is going to be another cosine. So it'll be negative cosine this time, but it's still going to give us 0. And then the fourth derivative, which is what we're looking for, is the last one, should get us right back to negative 1, because that should be sine. So we will now have a fourth degree Taylor polynomial created by these terms. So our Taylor polynomial of fourth degree first term, negative 1, plus 0 over top of whatever is just going to be 0. Our next term is going to be 1 plus 1 over, this is 2 factorial because it's the second derivative, x minus the center, 3 pi halves, to the second power. The next term is going to be 0 because it'll be 0 over top of the 3 factorial, so we don't need to write that. And then the last term is minus 1 over 4 factorial, x minus the center, 3 pi halves, to the fourth. This is our fourth degree Taylor polynomial. Again, not 4 terms, fourth degree. Again, very important that you understand the difference there. All right, so we want to evaluate this at 5 pi thirds. That's what we're trying to approximate. So we're going to have a Taylor polynomial of fourth degree evaluated at 5 pi thirds, which will be negative 1 plus a half. Now we have to do 5 pi thirds minus 3 pi halves. So the common denominator there is 6. So that's going to be, we'll just write this up here, that's going to be, you have to multiply this by 2 over 2, so 10 pi sixth minus 3 pi halves multiplying by 3 over 3, 9 pi sixth, so we get pi sixth. So we'll have times pi sixth squared. This is minus 1 over 24, that's 4 factorial, and then pi sixth to the fourth. Okay, so this is what you're going to plug in. You just plug this right into your calculator. Again, technically, you could work this out as it is and leave everything in terms of pi, but I'm more interested to see what the decimal is here so we can see how good of an approximation this thing is. If we plug all that into the calculator correctly, you should get negative 0.86605388334. And then if you just want to plug in, now you have to be in radians, don't forget that. If you just plug in sine of 5 pi thirds, of course we know the exact value of sine of 5 pi thirds is negative root 3 over 2. And then if you plug that into your calculator, you get the decimal approximation, negative 0.86600254038. So pretty close. This one's 4 decimal places accuracy, it looks like. And then it starts to differ a little bit there. Not too bad, though. Again, that's only 3 terms. It's a fourth degree Taylor polynomial. It's only using 3 terms. So that's a pretty decent approximation. You can imagine if this thing starts to use a huge amount of terms, it's going to be exact. And again, this is what your calculator does when it's evaluating these kind of decimals. It's exactly what it's doing. All right. Forgot that I separated all these things into different pages. This one's a little bit different. Use a fourth degree polynomial to approximate the value of natural log of 1.1. It tells us to use a fourth degree. typo there. Fourth degree Maclaurin polynomial. Now it does say it's a Maclaurin polynomial, so that means it needs to be centered at 0. Here's the problem with that. If we let our function, because it doesn't tell us what our original function is, we would assume, since this is natural log of 1.1, we would assume our function is the natural log of x. But how do you center natural log of x at 0 when your first term, natural log of 0, is undefined? You can't. That cannot be our function. But we can still center this at 0. We have to because it's Maclaurin. If we change our function to be the natural log of 1 plus x. This actually even makes more sense when you think about it, because now if you plug 0 in for x, you've got the natural log of 1, which is something we know the value of, and this is going to be really close to 1.1 since I'm starting with 1. So now we can go ahead and evaluate this thing. We do need to develop it. So f of x, or f of our center, f of 0, is the natural log of 1, which is 0. F prime, we're going to have to write this one out, I think, is 1 over 1 plus x. Evaluated at 0 is going to give us 1. F double prime, remember we need a fourth degree, so we need to go 4 derivatives. F double prime is going to be, let's see, if we make that 1 plus x to the negative 1, it'll be negative 1 over 1 plus x quantity squared. Plugging in 0 there is going to give us 1 squared in the denominator, so it gives us negative 1. Third derivative, so this is going to be 1 plus x to the negative 2, so multiplying that's going to give me positive 2, and then 1 plus x cubed in the denominator. Plugging in 0 here is going to give me 2, and then we will need a fourth derivative, fourth derivative, and that's going to be bringing that up as a negative 3 power. That's going to give us negative 6 on top. Reduce the power, subtract 1 from the power, give you negative 4, but putting it out on the bottom is x, 1 plus x to the 4th, excuse me. And then plugging in 0 in the denominator here gives us negative 6. So we have a fourth degree polynomial. It's a Maclaurin. You can use an m or a t, it doesn't really matter. Just to keep it consistent, I'll use another t sub 4. First term is 0. Second term is 1 over 1 factorial. And remember, this is Maclaurin, so it is x, not x minus anything, just x because it's x minus 0. The next term is minus 1 over 2 factorial x squared. The next one is going to be plus 2 over 3 factorial x cubed. And then the last one will be minus 6 over 4 factorial x to the 4th. There is our fourth degree Taylor polynomial centered at 0, so it really is Maclaurin. And now we want to evaluate the natural log of 1.1 using this polynomial as an approximation. So here's the trick. This function is the natural log of 1 plus x. In order for me to get the natural log of 1.1, I have to figure out what I need to plug in for x to get 1.1. Well, I already have a 1 here. So all I need to plug in for x is 0.1. So in order to evaluate this, x is going to have to be 0.1. Hopefully that makes sense, because if I plug 0.1 in here, now I get the natural log of 1.1. That's what I'm trying to approximate. So since x has to be 0.1, that's what I have to plug into x here. So I have a fourth degree Taylor polynomial where x is 0.1. That's what I plug in. Don't worry about the 0, it's gone, so this is just going to be 0.1 when I plug it in here, minus 1/2 0.1 squared. 2 over 3 factorial is 2 over 6, so that's 1/3. 0.1 cubed. And then 6 over 24 again is a 4th, so minus a 4th. 0.1 to the fourth. This one's not bad because you could technically do all this without the aid of a calculator, use some, long multiplication, stuff like that. We're still going to use the calculator to figure it out. So when you plug all that stuff into your calculator, this is what I got. 0.09538, and then a bunch of threes at the end here. And if you were to plug in the natural log of 1.1 into your calculator, you would get 0.095311798, I think. Pretty sure that's right. And so this one would have accuracy, it looks like, to also 4 decimal places. I think this problem in the past I've actually had people do, and they get something slightly different for either this approximation or the natural log of 1.1. Check it in your own just to see, but it's still a pretty good approximation one way or the other. Alright, so that's how you kind of evaluate or approximate something using a Taylor polynomial. And again, you can see we've only gone out to a 4th degree, and it's a pretty decent approximation. It's 4 decimal places. So now let's talk about this thing which is called the Lagrange error bound. Basically, it's a way to figure out what kind of accuracy we have to these things. Now, we've done it by creating the polynomials, but there's another way to think about how to do this, how to get the error bound. And it won't necessarily tell us exactly what the error is, but it's going to tell us a maximum error. So it's the most that we could be off depending on how far we go. The idea is the same as something we've talked about before. The idea is that if I take this first so many terms up to the nth term, obviously the infinite polynomials go past the nth term, but if we stop at the nth term, then we're going to have some kind of a remainder. As small as it may be, there's going to be a remainder. There's something that's left over if we just stop at the nth term. So the idea is, how can we bound this remainder so that we know that, okay, the maximum possible error is that remainder, is that what's left over there? Well, it comes from this. And what you should notice here, and this is the important part, is the remaining part of the function, the remaining part of our polynomial, is going to be less than or equal to the next derivative evaluated at our center over n plus 1 factorial x minus c to the n plus 1. So this whole thing right here is really just the next term of the Taylor polynomial. Let me kind of put this in better terms. Say I wanted to find a Taylor polynomial that had 17 terms in it. What you would do is you would look at the 18th term, and that is the biggest error that you can have for a Taylor polynomial. That's the general idea here. So the question is, how do we necessarily find all this? Well, there's some math speak here that we're going to go through. So you can read through all this, but really this is the idea. The next term, or the next derivative, is going to be the n plus 1 derivative. Whatever term we wanted to go to, we'll go to the next derivative evaluated at x. We're going to take the absolute value of that because we don't care if it's negative or positive. We just want to know how far away it is. This has to be less than or equal to, and we're just going to call it some capital M. Different books use different things. I think your book uses M. Well, this right here, that is that next derivative, is going to say, okay, if this thing right here is less than some M, then our remainder, or absolute value of our remainder, is going to be less than or equal to, since this is the next derivative, we'll just call it M, over n plus 1 factorial. And again, since we're talking about absolute value, we'll put this difference of x minus c in absolute values to the n plus 1. Again, all this is saying is this right here is the next term of the Taylor polynomial, where this piece is less than or equal to that next derivative at all times. All right, this is not necessarily the easiest of concepts, but hopefully after we do a few examples, it'll make some kind of sense. All right, we want to first of all use the Lagrange error bound to show that the approximation to the square root of e obtained by using a fourth degree Taylor polynomial for e to the x at x equals 0, which is really Maclaurin, is within 0.0005 of the exact value of the square root of e. So this is what we need to do. First of all, we need to figure out what e to the x is. This is a known series, so this is something hopefully you guys have looked at enough that you're going to start to get it memorized. But that's x to the n over n factorial. We can do that because this is a Maclaurin. It's centered at 0, right? Even though it says Taylor, it's Maclaurin. And if we write out the first so many terms of this, it would be 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, and that's all the further we need to go because we're talking about a fourth degree Taylor polynomial. So the square root of that, the square root of e is the same thing as e to the 1/2 power, right? Square root of e, equals e to the 1/2. So really all I'm going to do where x is I'm going to replace that with 1/2. So I'm going to get, by replacing it in here, 1 plus 1/2 over 1 factorial plus 1/2 squared over 2 factorial plus a half cubed over 3 factorial plus a half to the fourth over 4 factorial, and then I can just go ahead and plug that stuff into the calculator, and what I get out of that is 1.6484. Oh, I can't read my own writing. I don't know if that's a 3 or 7. I think it's a 375. This is what we get from approximating the value of square root of e using a fourth degree Taylor polynomial. The remainder is going to be the actual value minus whatever our approximation is. And we're going to do an absolute value on this because I don't care if it's positive or negative. The actual value, well, we can plug it into a calculator. We're just going to plug square root of e in, and what I get is 1.648721271. You may not have that many decimal places in your calculator, it just depends on your calculator, but this will be close enough. And then we'll subtract what we got for our Taylor polynomial, which is 1.648375, and when you plug that in and do the subtraction here, take the absolute value, you get 2.837 times 10 to the negative fourth power, which, if you realize, when you move the decimal place, that is the same thing as 0.002837. 0.0002837 is less than 0.0005. So that checks out. Okay, that's not so bad if it tells us what to do and we can actually just go ahead and do it like that. Typically, this is not the way it's going to work, though. So what it's telling us in example 2 is to approximate the function, the cube root of x, by using a Taylor polynomial of degree 2 at c equals 8. And then we want to know how accurate the approximation is. We've actually already done this part for the most part. But what we can do is we can find the Lagrange error, the error bound here. So we have to figure out what this function is first. So f of 8, and this is centered at 2, so we do, it's centered at 8, so we have to remember that. So f of 8, good news is the cube root of 8 we can do, that's 2. We need the derivative. Well, this is x to the 1/3 power, so we're going to get 1/3 x to the negative 2/3. Plugging in 8 If I plug in 8 here, it's going to be 8 to the 2/3. I'll worry about the negative in a second. 8 to the 2/3. So you could take the cube root of 8 first, which is 2, and then square it, which is 4. But that 4, because this is a negative exponent, has to get dropped to the denominator, so it's really going to give us 1/12. Okay, hopefully you followed that. And x to the negative 2/3. 8 to the negative 2/3, you do the cube root part first. So the cube root of 8 is 2. Squaring that, because that's this 2 part up here, is 4. The negative drops that 4 to the denominator, so 1/3 times a fourth gives you a 12th. Okay, the second derivative, and it does say we want a degree 2. So this is the furthest we need to go as far as the Taylor polynomial. This is going to be multiplying this, the derivative is going to be negative 2/9, reducing this by 1, x to the negative 5/3. And then plugging in 8. So again, the cube root part of 8 is going to be 2. Raising 2 to the 5th power, 2, 4, 8, 16, 30, it's 32. But that's got to drop into the denominator. Oh boy, I'm trying to do a bunch of mental math here. But the 2 over the 32 is 1/16. 16 times 9 is 144. So we're going to get negative 1 over 144 for our third derivative, evaluated at 8. Now, I know we're going to need this later because it is asking us how accurate the approximation is. So that means we need to find the error bound. We need the next derivative. Remember, that was part of, that's that m part. So we need the third derivative evaluated at 8 as well. That is not going to be part of the polynomial. It's going to be part of our error. That's a 4 here, by the way. 144. Let me erase that. That does not look good. There we go. All right, so our third derivative, multiplying these two things, is 10 over 27 x to the negative 8/3. And actually, I don't even need to evaluate this right now. Good, because it's not part of the polynomial. So let's write the Taylor polynomial of second degree. That is f of 8, which is 2, plus 1/12 over 1 factorial, x minus the center 8 to the first power, and then minus 1 over 144 over 2 factorial, x minus 8 squared. There's our second degree Taylor polynomial to approximate the cube root of x. So this is the approximation for the cube root of x. We are not supposed to evaluate this at anything. We want to know how accurate this approximation is going to be on the range from 7 to 9. Well, the idea is we got to figure out which one of these endpoints here is going to give us the largest degree of error. So in order for us to do that, we need to figure out which one of these things is going to give us the largest value when we plug it into here. You don't actually have to know the value right now, but what you do need to do is this. We need to know, first of all, that this third derivative is going to be less than or equal to our m. So what we're trying to find is our m. Well, if we did the third derivative evaluated at 7, that's going to be 10 over 27. Plugging 7 into here, that negative exponent drops it to the bottom, so it's really 1 over 7 to the 8/3 power. If I did this evaluated at the other endpoint, 9, because they're both the same distance away from 8, that's going to be 10 over 27 times 1 over 9 to the 8/3 power. I'm not worrying about trying to figure out what these are right now, but what I can do is I can figure out which one is greater. All of this is the same, the 10 over 27, the one on top is the same. So what that should mean is that the smaller denominator is the greater value, which means this one should be the biggest value, because 7 to the 8 thirds is going to be a smaller number than 9 to the 8 thirds, making this whole fraction bigger. So bigger denominator means, I'm sorry, smaller denominator means bigger fraction. So this is the one we're going to use. That is my maximum m value. So now all we really have to do is we have to plug this thing in. I know that my remainder, absolute value, of my second degree Taylor polynomial has to be less than or equal to this is our m value, 10 over 27 times 1 over 7 to the 8 thirds, over the next term. Well, we went to a second degree Taylor polynomial, so our next one will be a 3 factorial, and then the absolute value of, in this case, our x value that we used was 7, right? So 7 minus 8, so it's negative 1, but it's to the third power because it's our third degree term. So now you can plug all this stuff into the calculator, because believe me, we do not want to try and be doing any of this stuff in our heads. So when you plug that into the calculator, what you get is 0.000344. This is the maximum error of our remainder. So our accuracy, we can say, is less than, we could round this piece up to 4, so we could say it's less than 0.004 accuracy. So we should have an exact accuracy to 3 decimal places, and then within 4, what is that, tenths, hundredths, thousandths, 10,000, within 4 10,000ths. So this is our accuracy. This is the maximum error that we could have for our Taylor polynomial for the cube root of x if I only use a second degree. Still pretty accurate if you go in 3 decimal places before it changes. That's not bad. Alright, this video is running a little bit long. I apologize. I didn't know it was going to quite be that long, but it doesn't make sense to stop with only 2 examples left, so we're just going to finish it off from here. It'll be about probably 45 minutes or so, maybe a little longer. So example 3, approximate f of x equals cosine x using a Taylor polynomial of degree 4 centered at pi thirds. Use the Taylor approximation to estimate the cosine of 69 degrees correct to 5 decimal places. Alright, so first thing we're going to need to do is develop this, because again it is centered at something not 0, so we can't just use our known one. So f of pi thirds, cosine of pi thirds is a half. F prime, which is negative sine of pi thirds. Sine of pi thirds is root 3 over 2, so the negative of that is negative root 3 over 2. F double prime, which is negative cosine, will give us negative 1/2. F triple prime is now going to be positive sine, so that's root 3 over 2. And then the 4th degree should get us right back to the beginning, which is a half. So we have enough now to write our 4th degree Taylor polynomial. We do need to center it at pi thirds. So a 4th degree Taylor polynomial, 1/2 minus root 3 over 2 over 1 factorial x minus pi thirds, plus, nope, minus again, sorry, minus 1/2 over 2 factorial x minus pi thirds squared. Next one is plus root 3 over 2 over 3 factorial x minus pi thirds cubed. And then the last one is plus 1/2 over 4 factorial x minus pi thirds to the fourth. And what we want to find is an approximation for the cosine of 69 degrees. Of course, they gave us 69 degrees, which is not the same as pi thirds because it's not in radians. So what we need to do is we need to change 69 degrees into radians. All right, so 69 degrees into radians. 69 degrees is going to be the same thing as, let's see, you would have to change this into radians. It's degrees per radian, so 180 degrees per pi radians, right? So you can cross multiply. I'm going to get 69 pi equals 180 radian. So I can divide by 180. So our radian measure is 69 pi over 180. Let's simplify that. Looks like both things here are divisible by 3 for sure. 23 pi over 60. I don't think that simplifies anymore. So 23 pi over 60. We have to subtract pi thirds, which putting it in terms of 60, pi thirds is going to be the same thing, multiplying everything here by 20, so 20 pi 60ths. Subtracting these two gives you 3 pi over 60, which is the same thing as reducing that pi over 20. Okay, so you're going to plug pi over 20 in for each one of those. And when you do, because we are going to ultimately do a fourth degree Taylor polynomial at pi 20ths, when you plug pi over 20 in here, and believe me, this is going to be something you have to keep all this stuff straight. It's easy to miss something typing it into the calculator in your syntax. I got 0.35836866497. And if we want to check that this is actually within 5 decimal places, you would just simply type in cosine of 69 degrees. You can do that in degrees, or you can type in cosine of, what did we say 69 degrees was? 23 pi over 60. And from that one, I got 0.35836799495. But what you can see is that the first 5 decimals are identical. So we have found the Taylor polynomial accurate to within 5 decimal places. But of course it gave us all the information to do that. Alright, last example of all of Calc 2. Alright, the function f has a derivative of all orders for all real numbers x. Assume that f of 2 is -3, f prime of 2 is 5, f double prime of 2 is 3, f triple prime of 2 is -8, and f of 1.5 is this value right here. The fourth derivative of f satisfies the inequality of this. So it is telling us that the fourth derivative, which is not here, is less than or equal to 3. This looks like this is our m, if we need it, for all x in the closed interval from 1.5 to 2. Use the Lagrange error bound, yep, Lagrange error, so that's good, that's m, on the approximation to f of 1.5 to explain why f of 1.5 cannot equal -5. Well, that should be pretty straightforward. I don't actually think we need all this stuff, but let's see. If I know that m is less than or equal to 3, that's given to us here, then the maximum remainder of our third degree Taylor polynomial has to be less than or equal to that m Now let's see, they gave us the first three terms, but they told us this is the fourth, so this would be over 4 factorial absolute value of x minus the center. Now the center that we do need to pick up from this, the center is obviously 2. That's what we're evaluating everything at, to the fourth power. And it looks like we're trying to approximate f of 1.5, so that's what's going to go in for x. So the maximum remainder of a third degree Taylor polynomial at 1.5 has to be less than or equal to 3 over 4 factorial. Plugging 1.5 in here, you get negative 0.5 to the fourth. This value is equivalent to, plugging this into the calculator, 0.0078125. This is the greatest possible error. Well, if this is the greatest possible error, remember it's an absolute value, but if this is the greatest possible error that we can have, and this was the approximation, or the value, excuse me, of f of 1.5, if I take this value, and since it's negative, if I subtract this value, I should not be able to get to negative 5. So let's see if that's true. So it would be f of 1.5 minus the remainder of 1.5. That should not be able to get to negative 5. Let's see. So we would do negative 4.9583 repeating minus 0.0078125. And if you plug that into the calculator, you get negative 4.9661458, or something close to that. This value is greater than negative 5. And since this was our maximum error right here, that means that there's no way that I can add more or subtract more to these values. There is no way this would ever equal negative 5. So we have shown what they asked us to show. All right, a little over 45 minutes, but not quite 50. So there it is. There's 11.11, and good luck.